My name is Christian Carr, and I, along with my colleagues Emily Christian, Emiliano Venegas, Jordan Harrington, and Yannis Salcedo, will be presenting our report on a potential improvement for the hardware fuzzer called the HUZ. In the modern era, technology as a whole has become increasingly more complex, resulting in more and more bugs possibly going without notice and presenting vulnerabilities that malicious parties can exploit to leak data and hack into systems. Using techniques such as fuzzing, we combat these exploits by prodding for changes to hardware and software in a non-invasive manner. The fuzzer we are going over, the HUZ, generates assembly-level instructions and monitors any significant changes to increase the desired coverage of hardware designs in hardware descripted languages, or HDL. The HUZ features three components: a seed generator to produce new valid instructions made of configuration test inputs, a stimulus generator to mutate the new test instructions into illegal ones with an optimizer that tries to reduce the number of combinations that the generator creates at one time while keeping the coverage the same, and a bug detection mechanism that compares the outputs of the untested processor being fed to the mutated inputs with the reference tested processor's outputs. Any of the outputs that do not match the reference processor's outputs then indicate the presence of a bug, which then need to be manually analyzed.
Howdy, so I'm Yanis, and I will be going over a little bit of software fuzzing in order to understand hardware fuzzing. So, before hardware fuzzing, there was software fuzzing. Software fuzzing started with the problem that operating systems were not reliable and initially had a lot of security issues. A developer writes a unit test with multiple different inputs and checks to see if the correct output is generated. But this is not testing for every single test case, only ones that are known. So random inputs were generated to check for more vulnerabilities. But as it turns out, these inputs cause popular operating systems like Unix, Microsoft, and Mac to crash about a third of the time. This is where fuzzing was implemented. Software fuzzing uses statistical analysis as it looks at our program but never actually runs through it. It incrementally explores the program through random regression testing. This is when the program is bombarded with many random data to expose bugs and security risks. While traditional methods of hardware verification relied on formal verification and runtime detection, formal verification was not able to keep up with larger and more complex designs, and runtime detection was impractical and inefficient due to it only working in the fabrication process. As it should be known, hardware once deployed is patched up and therefore runtime cannot be ran. Therefore, software fuzzing was then adapted for hardware verification.
Going over the history of software fuzzing and the present applications in our presentation. So originally, software developers had to check and debug their operating systems. This relied on human programmers creating test cases, and then just seeing if they failed or not. The limitation of this was that if the programmer didn't know or was not informed of a certain bug that they couldn't test for, right, and slip through. So limitations of human testing were a problem when operating systems got larger and larger and more complex, where the amount of manpower you needed to manually debug these complex systems was not feasible, practical. So the first generation software fuzzers came to be in response to that. So the first generation were random regression testing, where is an algorithm based on going through probabilities like tree branches in the top left of probability like this path were taken, therefore combine that with different things and predict what was the most likely outcome, and that would create like expansive network of weighted options and to see which one is probably right. And that helped in creating modeling and trying to find these bugs that were unlikely to happen but were damaging. But the downside of this were that the model for random regression, it plateaus at a certain point, right? The probabilities, it's asymptotic behavior at the end, or flattens out, which is a problem. So the second generation were grammar and protocol fuzzers, where you would know the rules of the program, create an executable, and then monitor them with test values, right? And this could be defined through white box, where you know the algorithm and what it's testing it for, or you use a black box where you don't know what's going on inside, but it was more detailed. But is the limitation of trying to recreate problems. There are some that are both white and black box, but that's outside the scope of this assignment. And now the third generation that creates guided fuzzing that generates an input, like watches from the input, mutates it, and then creates coverage for the program. So the HUZ in this in our project does just that. So it creates valid inputs, mutates them, and then sees that, hey, does it create a certain mapping? How much of the circuit lights up when we put these inputs in, right? But the special thing is to prevent the bloating. That having overlapping coverage, as you can see in the bottom right. Imagine those circles are how much of the circuit lights up of all the possible ideas. So you have overlap of two circles, right? But if you have one pathway that lights up both of them, right, you would cull the inner ones, right? And that's the power of the HUZ, is that not only does it mutates and records the mutations, it also can self-check and be like, hey, do I already have something that's a little bit better than this? Let me just keep that and then remove the things I already done, right? So that's the power of the HUZ. And why it's relevant is that software bloating and performance issues can happen. That's how software fuzzing and the HUZ gets around this. So yes.
Howdy, my name is Emily Christian. I will be presenting the slide covering the topic of setting up and improving the HUZ. The HUZ is a tool designed to find bugs in computer hardware. Setting it up starts with installing it on Olympus server using pre-written setup files. We organize everything so the tool runs correctly during experiments. Testing is done using 3 processor simulations: Rocket Core, Boom, and CVA6, which act like virtual processors to mimic real-world conditions. To improve the HUZ, we focus on 3 areas: how many bugs it can detect, how quickly it can find them, and how fast each test runs. Faster and more efficient tests mean more bugs are found before they cause problems. We test 2 specific features to try and refine the HUZ in accordance with these standards. Those features are the branch coverage, which makes sure all parts of the hardware are tested, and the toggle coverage, which tracks signals to ensure the testing is thorough. This process helps us improve the HUZ to make it more effective at finding and fixing hardware issues.
My name is Jordan Harrington, and I'll be covering the results. So for the CVA6, we had about an average coverage of 36%, and the runtime was a little over a minute. For our first modification, with both being 5, we saw no significant improvement in the coverage or runtime. But when we changed the modification to both be 2, we saw a significant improvement and an increase in the coverage, a slightly slower runtime. For our RC analysis, our base average coverage was 46% with a runtime of about 42 seconds. And then both of our modifications failed to show any significance. For our boom analysis, we had about an average coverage of 47% with a runtime of a little under a minute, and both modifications did not show much improvement. We found that for the low sample sizes, our RC modification with the 2s had the best balance of coverage and runtime efficiency, and the boom baseline average trends offered a higher coverage, but also had higher demands computationally. For our large sample size, we saw that the coverage plateaued around 600 samples, roughly the same for the RC and the boom test, and then much lower for the CVA6, showing that the RC and boom outperformed the CVA6 in our high sample test.